Continue with Duffing equation, and we will study chaotic solutions. And we will use Poincare sections and the Poincare map. And as I have discussed in a previous lecture, the idea is you have a Q1 and a Q2, let us say some state space, except there is periodic forcing in time, so you come forward to time t. Q dot is f of q and t, and this is t periodic. It's time periodic. So what you do is you map the state forward. So you start from some point here, map it forward, and that point you project back, and then you map it forward, and that point you project back and you map it forward, and that point you project back and you map it, well, maybe that one comes somewhere here, and you map it forward, and that point you project back, and so on. And in this way you get a very large number of points here, which forms a complicated set. Okay. Now if you think of a tube of initial conditions, this tube as it comes along may shrink in cross-sectional area because of damping, but at the same time it may get stretched and folded in some funny way. Okay, and then that gets mapped here, and then it comes forward, and then it shrinks further in volume, but it gets stretched and folded again. Okay, and so one way to see that is to first look at this set of points and see the very fine structure it has and the self-similar structure that it has. And so we will move to MATLAB now, where I have changed the parameters slightly from the last lecture, but that's just gives a more damping, and it still gives these chaotic solutions. Let me show you some solutions. So over here I am starting, let me start. So now 0.6, right? So omega is 0.6, so I want an integer number of periods, but let me do 100 periods, and then over here I can have a lot of points, it doesn't matter, and then some random initial condition. So I run that, and then I can plot tx1 to show you what the solutions look like, and you can see that like before they are irregular looking solutions, and then once we zoom in you can see that there is this sort of peculiar irregularity to it, and this is the steady state behavior. Okay, so if you now want to look at the Poincare section, I have generated a lot of points in a previous calculation so that we can look at those, and here they are. And if you let's make it bigger, so you can see that this looks like a line here, right? But it isn't. If we zoom in, so if we look at this portion here, if we zoom into this portion here, you will see that there is a lot of structure there. And if we zoom into this portion here, this little loop here, then you will see that there is a lot of structure in it. And if we zoom in, we will see more and more and more structure. The fine structure never ends. Over here it will end because I have a finite number of points, but if I had an infinite number of points, in that case the structure would continue to be seen no matter how much I zoomed in. Suppose I zoom into this portion here, you will see that it has all this structure here. Suppose I zoom in here, you will see that it has all of these loops. Okay, over here you see all those loops, and then if you zoom in here it will be similar, If you zoom in here, it will be similar, and if you zoom in there, it will be similar, although now I am running out of points. I didn't have enough points in my calculation. If you just zoom into this portion here, this line here, if you zoom in here, you will see that there is structure over there. Looks like two lines here, but you zoom in and it's not two lines, and so on and on and on till infinity. Okay, now where does this kind of peculiar behavior arise? Okay, so one way to see that is to do a different calculation, and for that we have to go back to the Poincare section. Only remember that the only criterion is that the distance in time between the Poincare sections should be t. But of course I could take another one. I could take maybe a section here and move it forward t and to another plane here, and then over here I would get a slightly different set of points. Okay, so if you think of all those trajectories, think of the orange lines, think of millions of them going forward. You can think of them as maybe the hair in a girl's braid, you know. So there are all these fibers that are going through like that, and they may be twisted in various ways, and in that case we can consider sections here, then another section here, then another section here, then another section here. And so instead of taking one trajectory, let me make a fat line here with red. So instead of following one trajectory like this, we can instead take, let me take a fat green one now. We can take this plane with all those intersection points and slowly sweep this plane forward and see how that set of intersection points changes. And I have done that calculation also and saved it, and here is that figure, and maybe I can make it a little bit bigger, just a bit bigger, but not too much. This much is all right. I should be able to move it, maybe not. So okay, we will just stick with this. Now if you look here, although it's a bit small, the parameters are the same. F is 1.3, omega is 0.6, C is 0.2. I hope you can see my cursor. So you can see this is the Poincare section, and slightly later phase this is the Poincare section, and slightly later phase this is the Poincare section, and so on. And you can see that this curved part over here seems to be shrinking. This part is sort of elongating and folding over. You can see this one folding over and this one stretching. So this one folds over here. And now this loop over here is beginning to stretch, you see, while this one is folded over and got very close. So if you look at this loop here, you see how it is getting very close, and you see this part here, it folded over, but then the single part of it stretched out and out and out and out, and this bent part over here is sort of coming around, and you know, then you will, when you look through this in detail, you will see a very similar sort of almost symmetrical transformation of this shape on the other side. So you will see here, this one bending over like this, and then stretching, that one stretching the other way. This bent over part is now, you know, further bent over like this, and you think it is now one, but it started over there. Okay, so in this way, as it bends and stretches and bends and stretches, overall its volume shrinks, but this is the source of the exponential separation of nearby trajectories. So let us just think about it a little bit. So suppose I have, you know, some set of points here. So it's right. So then what happens is this part stretches, and I have something like this, but it has shrunk laterally. it's narrower, its total area is smaller, right? So then it goes like this. And then the whole thing again, let's see, I have to draw it a bit carefully. The whole thing bends over like this, and then you see this part is beginning to look like this part, and you do this infinitely many times, and then you get some extremely fine structure. Okay, so that is the attracting set. We have got only a small picture of it, but you know, with a finite number of points, but there is a very fine detail in there, and nearby trajectories are all attracted to that. And this is a complicated set. It's called a fractal set, as I told you earlier. Let me show you a simpler equation in MATLAB, which is called the logistic map, and it has very similar behavior. Okay, so let me do it like this. I will do it in two ways, so you need to pay attention to the MATLAB commands I'm using now. So we have a parameter. This parameter can be, you know, something 3.85. 4 is the maximum. So here is what we will do. I will say x is equal to zeros 1E6 1. So I have 1 million points here. Then I will say x1 is equal to, no, let me do the following. Xx is equal to rand. Let me take mu is equal to 3.9 as some number, and then let me say x for k equals 1 to 100. Xx is equal to mu times xx times 1 minus xx. End. So I have, this is the map. Okay, so the logistic map is this. This here is the logistic map. Let me make the brush size a bit thinner. This is called logistic map. That's a bit too thin, maybe a bit more here. Logistic map. Okay, xk plus 1 is equal to mu times xk times 1 minus xk. Okay, this is not the solution of a differential equation. This is just a map from one state, state k, to state k plus 1. Okay, so that's the logistic map. You can see here that I have chosen a random initial condition. I've chosen some value of mu based on prior experience, and then I am doing this map, evaluating it 100 times. So that gets rid of transients. And now what I will do is I will say x1, or let me do the following. For k equals 1 to 1e6, and then I will evaluate this map again, and then I will say xk is equal to xx. So let me store 1 million of these. Okay, so 1 million was not a very large number, so I've got it quickly. Let me look at the histogram of x with maybe 1,000 bins. Okay, and you can see that the histogram is quite complicated. There are places where I hope you know what a histogram is, but you know, there are places where there are many points, and there are places where it seems to be there, you know, just a density. Now, what is this peculiar histogram? This peculiar histogram is what, you know, that's how the points are moving on some attracting set, right? Now let me do the following. Let me save y equals x. Okay, and now let me continue this solution, right? So what I will do is, it's very easy. I'll just continue from the last value and get another million points. Okay, so I just rewrote over the whole original points, and now let me do subplot 2 1 1 histogram x 1000 subplot 212 histogram y 1000. The point is, well, that didn't work. That didn't work because this has to be 212. Okay, so now the point is, you see, I hope you will agree that the histograms are the same. Okay, now this histogram is generated for a particular value like 3.9. If I change mu, it will be a different histogram. But more interestingly, I have obtained it from one long transient. Okay, so let's do a different calculation. Let's do this calculation. Let us say x, well, let me say z equals x and save that. So y and z have two different series. Y and z are not the same. If I look at x 1 to 10 and z y 1 to 10, these are not the same points. These are completely different points. It is just that their statistical properties are the same. So for example, if I say capital X is equal to y and z, right? So now if I say the mean value of x, they are the same. This difference is because there is a finite number of points, right? If you can look at statistics, you know that the sample mean will differ from the true mean by the standard deviation of the population divided by the square root of the sample size. The square root of the sample size here is 1000. Okay, so we have that. So now we can also look at the standard deviation of x, so of the two, and you see that they are again basically the same. Okay, so these two series have very similar time series. Let me show you something else. Let me plot xk plus 1 by xk. So CLF, and you see I've cleared the figure now, and then I say plot x from 1 to end minus 1, that is the independent variable, and x from 2 to end. No, that didn't work. That didn't work because it joined it with straight lines. I should plot them with dots. Okay, so there you see that is the parabola. Over here, even if I zoom in, I won't see any particular structure. That's all. It's just a single line. Okay, that's all it is. There's nothing there. Okay, this is the parabola. What is this parabola? This parabola is nothing but x 1 to end minus 1, and then 3 point, I think I used 9, mu is 3.9, mu times x from 1 to end minus 1 times dot star 1 minus x from 1 to end minus 1. And this one I can plot with a red line here, except I have to plot it with dots, otherwise I'll get into trouble. And then, no, I don't have to do that. Here's what I will do. I'll say xx is equal to ln space 0, 1, 200, and then over here I have to use xx, xx, and then this can be a red line. Okay, so when we look at that, you will see that it is basically exactly the same. Okay, that is what it is. We have evaluated the map. There is nothing. But when we look at the sequence, then there is this peculiar structure, and this is how the points are distributed. The more important thing that I was telling you earlier, let me just emphasize again. So if I take this histogram and I show you this histogram, it is the density of points where we look at one time series. But suppose we do a million simultaneous experiments instead. Okay, so let us say x is equal to rand. Initial conditions have to be between 0 and 1. So 1 is 6, 1 by definition for this model. So each is a random initial condition, right? Then I say for k equals 1 to 100, and then say x is equal to mu times x dot star 1 minus x. Okay, so this is a million simultaneous trajectories. I am doing it 100 times so that transients are removed. Maybe I'll do it 100 times again. Transients are clearly dead. Okay, now let me do the histogram, and it is the same. Okay, so this is another thing that is very interesting about such systems, which is that if you look at one time series, one trajectory, and let it evolve over a long time, then the statistical properties of its behavior that you observe, for example, the total amount of time it spends between 0.4 and 0.43, or its, the average value of its square, or whatever it is, whatever statistic you compute. So on this set will be calculated based on basically the probability density function, or in this case, because there are singularities, the probability measure. There is an invariant probability measure on this attractor. Those are the technical terms. You have to read further to understand these things, but I will not dwell on them in detail. So this invariant probability measure, or this invariant measure on the attractor, it can be obtained equally and equivalently in two ways. One is by looking at one trajectory for a very long time, or the other is to look at many simultaneous but independent trajectories. So the loose way of saying this is that the time average is equal to the space average. Okay, and this property, time average of whatever quantity of interest that requires the probability measure on the attractor, or so time average, this is a very loose statement of the same thing. This property is called ergodicity, and it is important and common in chaotic systems. Okay, so that's one more point. Now let me do something else. One more thing to show you. So here I have, let me close the figure. Let me say plot x and xx. Well, let me not do it like that. Let me say x1 is equal to linspace 0, 1, 2000. Okay, and let me say x2 is equal to mu times x1 times, dot star 1 minus x1. So now the map can be graphically drawn like this: x1, x2. This is not a surprise to you at all. This you know that it is this parabolic map. It is called a unimodal map because it's got one maximum in the middle. However, imagine that I just evaluate it twice. So then I have x3 is equal to x2, mu times x2 times 1 minus x2. So this is two evaluations of the map. And then because I am evaluating the map many times, I can just look at it two evaluations at a time, and then it looks like this. Okay, now let me just remind you that I can also plot x1 and x1 over here to show you what the original value is. So for example, if I start at x equals 0, I evaluate twice, I'll stay right there. I start at x equals this particular value, whatever that is, and I'll stay right there. I can start here. So these are 4 fixed points, but these are unstable fixed points. Okay, so what happens is, at this value I evaluate the function twice, I come here, then I set that to be the new value of x, then I go here, then I evaluate the function and I go here, then I set that to be the new value of x and I go here, I evaluate the function and I go here, I set that to be the new value of x and I go here, evaluate the function and go there, set that to be the new value, evaluate the function, set that to be the new value, and this is how I bounce around. Okay, so you can see that there are extreme complications that can arise from such a map. This is why the logistic map has been studied a great deal by very talented people. There are absolutely wonderful things that are known about it, but the simplest thing that should be seen about it, I should do that for you first, and we will stop there with the logistic map. So here it is. Okay, so if I say xk plus 1 is equal to mu times xk times 1 minus xk. Okay, so now of course if mu is more than 1, then near the origin this one goes like that and this goes like that, and so I know that I have some stable point here, so I want mu greater than 1. Okay, but then after that what happens is, very soon as mu gets bigger, right, the intersection occurs here, and over here when this slope becomes less than -1, that means the slope is more than 1 in magnitude, that is where stability is lost. Okay, so let us start with mu equals 1.5 or something, and that should be all right. But what I will do is I will increase mu very, very slowly. So I will increase mu from 1.5 to 4 in 1 million steps, and I'll just keep following the x trajectory, and then we will look at the figure. Okay, so this is the last simulation. What I will do is I will say x, let me say mu equals linspace 1.5, 4, that's the maximum, 1e6. Okay, so I've got that, and then I say x equals zeros, 1e6, 1. Oh, that's just to declare it. I say x equals x1 equals rand, so I seed it with something random. Then I say for k equals 2 to 1e6, right, and then I say x k is equal to mu k times x k minus 1 times 1 minus x k minus 1. So now what is happening is I am changing mu slowly. So this I am generating what is called a bifurcation diagram. Okay, and then what I can do now is I can plot mu on the horizontal axis and x on the vertical axis, and we will get the bifurcation diagram. So this is a very famous diagram. I've drawn it badly because I have got lines here. So let me do it with dots first. So now this is a very famous diagram, and over here there is a small delay in the loss of stability. Okay, so if I sweep it more slowly, in that case this gap will go down. So let us see how much this gap is. This gap is from 0.62 to 0.7. It's about 0.08, this gap here. So now let me do it more slowly. So let's say mu equals, and over here let me take 10 million points, right, and then let me say x equals 10 million, and then let me say for 10 million. Okay, so now I'm doing it more slowly, and then if I plot this diagram, well, that didn't work. Oh, That's because I started with zeros. I have to say x of 1 is equal to rand and then do it again. And you see now this gap is a bit smaller. Now it is about 0.05, right? So it has become smaller, and in this way it will get smaller slowly. And if I take more and more points and sweep it slower and slower, that's not really the interesting part. The interesting part is here is this period 2 bifurcation. Period 2, why? Because over here this slope became -1 and then greater than that, and so we will get oscillatory solutions over here. Okay, but then the slope keeps increasing, and then even that period 2 becomes unstable. Okay, so then it becomes a period 4, then it becomes a period 8, and there is in fact a period doubling cascade of bifurcation. So 4 becomes 8, becomes 16, and so on. And then there are these special structures over here. There are periodic windows. Okay, there are periodic windows. These are stable. There are infinitely many periodic windows, and there is a great deal that is known about it. Okay, there is something called Sharkovsky's theorem. I will not tell you what it is. I don't know how to prove it myself, but you can look it up, and it's an absolutely stunning result. Okay, so but when we look at one of those values, like I was using 3.9 earlier, so you look here, let us say that's 3.9, somewhere in here is 3.9. Okay, so when you look there, even at 3.9, we were lucky. At 3.90 something, there is a periodic window. Over here there is a periodic window. Actually there are many periodic windows, but most of them are very thin. So we were at 3.9, and then if you look here at 3.9, if you look at the density that we have for 3.9, so you can see that they are more dense here, and then maybe not so dense here, and then more dense here. And you can see, there are other patterns over there. You have to think about that later. But the range is from 0.1 to 0.9, something in the high 0.9s, and that is roughly, it should be exactly actually, but anyway, consistent with the range here from 1.1 to high 0.9s, and on the high side there was greater density, in the middle it was emptier, and so on. Okay, so that is an example of an invariant measure on an attracting set, right? But of course this is a one-dimensional set, and then the final set is also one-dimensional, so that is a little different from the Duffing oscillator. But for the Duffing oscillator, for the Duffing oscillator, for the parameters we used, we had this kind of complicated set. This is, one of these is x, the other is x dot on the Poincare section, and it's a more complicated set. And you can see that it has actually, it does not have non-zero area. Its area is 0, right? It's just a set of some fractional dimension. It is not a point, right? So then there are ways of calculating the dimension, and I don't want to say what it is, but I imagine it's between 1 and 2. Okay, so there are different ways of calculating the dimension. I have not calculated it. I will not say what it is, but you can say there is some complicated set here. There is an invariant measure on it. That invariant measure corresponds to, higher density and lower density at different places. Okay, so you can see that the density itself is sort of a wildly irregular function, right? It's highly irregular. Over here, more points have to be filled in for you to see the details. So let me summarize then. Okay, so few things. One, we have continued to look at the Duffing oscillator. And in the Duffing oscillator, over here, if we take one of these planes, let me take a fat brush again to help to emphasize the point, if we take one of these planes like this one and we look at the points, we map forward and come back, map forward and come back, map forward and come back. So we do that, and when we generate that set of points on this plane, so that's the this plane is the Poincare section. But to understand how these different strands are woven together, we can also take this plane and sweep it forward. And I have done that for you and shown you this figure here. And when we sweep it forward, then you can see this stretching and folding. It's qualitative, but you can see the stretching and folding. And the stretching and folding has the following consequence. It is somehow very important for chaos in flows. Is, you stretch it and fold it, you stretch it and fold it, the area goes to 0, length goes to infinity, right? And what happens is nearby solutions. So in the part that is being stretched over here, nearby solutions diverge exponentially. Why exponentially? Exponentially on average. Why exponentially? That is because, let us say you have 2 points over here, and every time you come to this phase, basically it is doubled in length. So that's a factor of 2, then a factor of 2, then a factor of 2, until they are here. One is here and one is here. And after that, what happens is, they sort of go far away. So then one is here and one is here. They've gone far away. But then this bend occurs and they sort of come close again, right? And so you will see, if you look at log of separation by, iteration number, then you will see something like this going approximately linearly until it becomes comparable to the attractor size. And we have seen this kind of figure yesterday from numerical simulation. There is something called a Lyapunov exponent, which is this average rate of separation, that we will do later. Lyapunov exponent, we will do that one later. Okay, and so the idea of the invariant measure, read about that. About the logistic map, read about that. The bifurcation diagram I showed you, which was, like this and like this and like this and like this. These coincide, they are all in the same vertical line. So this bifurcation diagram, read about bifurcation diagrams. In this course, we will cover these at the level of doing some calculations and generating some things and discussing their features, but we will not prove them rigorously, because a different set of tools is needed and a full course is needed at the very least. That's all for today. Thank you.